Up to this point, we've been taking multiple vectors, two or three typically, and resolving them into a single force, finding a resultant, adding them up, in other words. And that's been the solution to the problem that we were trying to solve. But a lot of times, it's best to solve a problem by taking a single force and resolving it into two parts. And that makes it easier to solve our problem. This is a classic case of such a situation. An object accelerating down a frictionless ramp. So here's a ramp. We're going to pretend it has no friction. It's like super slippery, so slippery that there's no friction at all. We're going to change that eventually, but we don't know much about friction yet, so it's going to be frictionless. Now, this object, as you all know, if you set an object on a steep ramp that's slippery, it is going to slide downhill. It slides downhill and accelerates. It's going to go faster and faster and faster the farther it goes down the hill. Well, because F is equal to ma, we know that there is no acceleration without some kind of a force. What's the force? Well, if we draw a free body diagram, we're only going to be able to identify two forces. One of them is gravitational pull. So the force due to gravity, in other words, the weight of the object, Fw or Fg, you might say. But if that were the only force acting, then it would have a net acceleration in the direction of the net force, which would be straight down into the center of the Earth. And we know that isn't happening with these ramps. So there's got to be another force. And if we think about it, this is what it is. It's what we call the restorative or the reactive force of the ramp. The ramp itself is exerting a force that keeps the thing from falling straight down. Well, the object is staying on the ramp, however, so even though there's a force, this reactive force that we identified in the last slide, that's pushing up, there must also be a force that's equal and opposite that's pushing down, because we don't notice any net force in this direction. It's not flying off the ramp, it's not sinking into the ramp. So we have this component, part of the weight, that pushes down into the ramp, and scientists call that the normal force. Force normal. And normal doesn't mean, not weird or ordinary. Normal in this case means perpendicular to. So this is perpendicular to the ramp, the normal force is. But if that was the only part of the weight that was there, it wouldn't slide down the hill. So there's got to be something else going on. The rest of the weight, the rest of the force due to gravity on this object is directed down the hill, and we call that parallel force. And the parallel force is what causes it to accelerate down the hill. So this is the part that's equal to m times a. So it doesn't accelerate at the acceleration due to gravity. It's at something less. If we wanted to know what that acceleration was, we'd have to know the size of that parallel force, because F equals ma. So let's take a look at that. In solving this problem, one of the things that we find makes a lot of sense is to make a convenient axis system. You can choose your axes anywhere you want to, and so we can have our axes, instead of being like horizontal and vertical, we'll just tip them enough that one axis goes down the ramp and the other axis is perpendicular to the ramp, because it's the parallel force that we're really interested in knowing about. So when we do that, we find that our weight, we'll call this Fw for weight, that's just equal to this vector, which turns out to be our normal force, and this vector here, which is our parallel force. They're just the components of F of g on these two axes. Well, our strategy that we've used involves finding out what these angles are. This is adjacent to that angle, and this, if you slid it down here, would be opposite that angle. So we already have strategies for figuring out the size of these. Okay, let's try and figure this out. Let's first work with force normal. So I've got force normal that's going down the n-axis, and it is a component of the weight. So I'm going to put Fw for weight, Fn here. I want to know what is Fn in terms of Fw. Well, one of the things that I know is this angle here is going to be important, because this is adjacent. Fn is adjacent to this angle, and so it's going to be related to the cosine of that angle, whatever that angle is. So I'm going to call this angle theta. Now, looking at the ramp itself, let's give this angle the name alpha. Let's say that's the angle of the ramp. Well, up here, if I continue to extend this line down, I make a 90-degree angle with the horizontal, because that's going towards the center of the Earth. It's weight, it's gravity. So the angle up here on this triangle, that angle right there, Well, that's going to have to be 90 minus alpha, because alpha plus 90 plus that angle have to add up to 180. So that makes it 90 minus alpha. Now, if I look at this, the parallel direction compared with the normal direction, well, that's a 90-degree angle too. So I'll reproduce that over here. Here's parallel, here's normal, here's vertical. That angle is 90 minus alpha. That angle, which we're calling theta, well, it's 90 degrees all the way across here. 90 minus alpha is just alpha. So that means theta really is alpha. So the angle of the ramp is that angle in there. Let's clean this up. Now, knowing that, I can quickly determine what is my normal force. If this is force due to gravity, or FW maybe for weight, and this is normal force, and this angle here is theta, which we now know is the same as the angle of the ramp, the force normal is equal to the weight, FW, times the cosine of theta. Let's figure out force parallel. Again, force parallel is the other component of the force due to gravity, or the weight. But it's down in this direction. Now, if I take this vector and I just slide it down here, I can make another triangle. I'll duplicate that over here. FW, force parallel. Now, here's my N axis right there, Fn, and that angle in there is theta, which, remember, is the same as the angle of the ramp. Well, now Fp is opposite theta, so that means my force parallel is going to be equal to my weight times the sine of theta. So we can make these two general rules. These are shortcuts. These are things you might want to put in your toolbox that are relevant for ramp problems. Now, don't try and use them for other things, because they're specialized tools. They're only for ramp problems. But the normal force is the force of gravity, or the weight, we called it in the example, times cosine theta. And the parallel force is going to be the weight times the sine of theta. Let's apply that. 2 kilogram box is allowed to slide from rest down a frictionless 7-degree ramp. What is the parallel force on the box? So here's my ramp. Here's my box. This angle is 7 degrees, and my objective is to find the parallel force. Well, here's what the weight is. Fw is m times g, which is going to be 2 kilograms times 9.80 meters per square second. That's kind of the definition of weight. Now, if I figure out what that is, then 19.6 newtons. That's the weight. But we know from our toolbox, from the last derivation that we had there, is that the parallel force is going to be equal to that weight times the sine of our angle, which in this case is a 7-degree angle. So our parallel force in this problem is going to be 19.6 newtons times the sine of 7 degrees. And that comes out to 2.4 newtons. Now from there, you could find the acceleration down the ramp. And that's what this question is asking. Same box, same ramp. The question is, what's the acceleration of the box? Well, we determined in the last slide here that force was equal to 2.4 newtons. That was our force down the ramp. And force is equal to m times a. So that means acceleration is force divided by mass. Well, that's 2.4 newtons, or 2.4 kilogram meters per second squared, divided by the 2.0 kilogram mass. Kilograms drop out, and we'll end up with an acceleration that's just meters per second squared. Now, you may have noticed that we first multiplied by mass in a previous part of this problem, and then we divided by mass. So obviously there's a shortcut here. probably you can figure out what that is. So if I take my 2.4 and divide by 2, my answer will be 1.2 meters per square second. So that's the acceleration. Well, the problem's expanding. Still a 2 kilogram box, same ramp, same slope, still frictionless. We want to now know what's the speed of the box after it has slid for 5 meters. Well, we have a couple of equations that involve final speeds. This is probably the one that's going to be the most useful here. Vf is the square root of Vi squared plus 2 times A times D. If the thing started from rest, then this term is 0. So this just simplifies to 2 times A times D. And we now know that our acceleration is 1.2 meters per square second. And it's telling us that it's going for 5 meters. If we multiply these two terms together, the units are going to be meters squared per second squared. But when we take the square root of that, that's just meters per second. I come up with 3.2 meters per second. So after 5 meters, that's how fast it's going. This question asks about the same box on the same ramp. How far does the box slide in 15 seconds? Well, from our toolbox, we have this equation that might be more relevant here. Distance is Vi times the change in time plus the acceleration over 2 times the change in time squared. Once again, this term goes to 0 because there's no initial velocity. It's 0. So the distance it slides is going to be the acceleration, which we know to be 1.2 meters per second squared, divided by 2, times the time, which is 15 seconds, squared. Square seconds are going to cancel. Distance will come out in meters. When I do my calculation, here's what I find. 135 meters is how far it's going to slide.